In this lecture of Earth motions, we're going to be doing some astronomy applications of circular motion. So we can first talk about rotation and revolution. So what's the difference? Well, the Earth's rotation is what is going to be leading to day and night. That half of the Earth is going to be called what we call illuminated, and we call it daylight. So it's the day and night is the result of the Earth's rotation, that the side experiencing daylight is facing the Earth. So the other half, or the other hemisphere that is facing away from the sun, is experiencing darkness. So seasons are the result of the Earth's axial tilt at 23.5 degrees as it orbits around the sun. And this is what is going to then change the directness of sunlight. And this is what's going to then lead to the amount of heat that's going to be influencing the seasons. So the seasons are kind of a feature or factor of both the axial tilt and Earth's orbit that's then going to change the amount of directness of sunlight. Moving on. So this picture is not to scale. The Earth makes one full rotation each and every day. Rotation is around an internal axis. And in a calendar year, the Earth makes one full revolution around the sun. So we can start looking at these four noteworthy locations in the Earth's orbit, or in the Earth's revolution around the sun. So in the picture to the left, one can see how incoming sunlight strikes the Earth at different angles. The more direct the energy, or the sunlight, the greater the heat energy per unit area. The lower the angle, the less energy per unit area. So here I'm going to have you locate and identify the solstices and the equinoxes in the picture above. So the summer solstice is June 21st and the winter solstice is December 21st. So let's find where the summer solstice for the northern hemisphere is in June 21st. That's where the sun is going to be the highest overhead. So we're in the northern hemisphere, and you'll find that over here the northern hemisphere is tilted towards the sun. Therefore the Tropic of Cancer is receiving the most direct sunlight. This location over here is June 21st. Well, 6 months later, we're going to find that the northern hemisphere is tilted away from the sun. This is going to be what we're going to call our winter solstice. This occurs on December 21st. This is when the Tropic of Capricorn in the southern hemisphere is experiencing a sun that's directly overhead. That the Earth's longest and shortest daylight hours of the year come on the solstices. In the summer, or the longest day is June 21st, the summer solstice. And the shortest daylight hours is the winter solstice, December 21st. But we also have two periods of time, or two dates, in which the Earth is experiencing equal daylight hours, 12 hours of daylight, 12 hours of darkness. And these are called equinoxes. And we can see them here, and we can see it here. In this side you can actually see how the arrow is pointed toward the equator. And it's just saying that all points on the Earth are receiving 12 hours of daylight and 12 hours of darkness. And those are called equinoxes. So when we go from summer, here we have the fall equinox, here we have the winter solstice, we have our spring equinox, etc. In the picture here to the left, we can see incoming sunlight angles that determine how much heat energy is reaching the Earth's surface. You'll have to forgive my son's in here playing, so. Yeah, Bubba. And here we see that the most direct sunlight is reaching the Earth's equator, and we would say that this is an equinox. Here we have the most direct sunlight right here at the Tropic of Cancer. This would be the northern hemisphere summer, or summer solstice to be specific, June 21st. And this one down here would be the winter solstice, where the Tropic of Capricorn is receiving the most direct sunlight. So if I look at this picture right here, this is a picture of the winter solstice, where 23.5 degrees south, the Tropic of Capricorn is experiencing the most direct sunlight, and the northern hemisphere is experiencing winter. So the way we perceive the sun traveling through the sky, the arc, is going to change throughout the course of the year. Here's how. Both pictures above illustrate the same thing. In the summer, days are both longer in daylight hours, and the northern hemisphere receives more direct sunlight. In the winter, daylight hours are shorter, and the northern hemisphere receives less direct sunlight. So in the winter solstice, in this case, this would be, when this says winter solstice, you have to be careful, because this would be talking about the southern hemisphere picture here. I didn't catch that before. But we can still use the angles to see this. In the winter, the sun's going to be lower. So if we're in the southern hemisphere, we're going to see that the or well, we live in the northern hemisphere. So we're going to see the arc of the sun at a lower angle in the winter than we are going to see it in the summer. The summer is going to be, it's going to rise sooner in the morning, it's going to set later, and it's going to end up higher in the sky. And throughout the course of the year itself, it's going to change. Each day the sun is going to take a different path. And that's just from one calendar, through one calendar year. It's going to go from a low angle, it's going to be getting higher, eventually reach the equinox, and eventually going to reach the summer solstice, and then it's going to start getting lower in the sky. And so we see the sun's zenith, or the highest point, it's going to change along with the arc itself. So in the winter, the daylight hours are shorter. It's shorter because it rises later and sets sooner, and it doesn't ever get as high. So that's going to change. It's going to decrease the amount of heat energy. So if I look at it in terms of heat energy, if I look at this location right here, this is going to receive very, very direct sunlight angle. That heat energy is going to be over a much smaller area. But if it's at an angle, that heat energy is going to be spread out over a greater area. So notice if it's directly overhead, right, the higher the sun is in the sky, the more direct the sunlight. So when it's higher in the sky, the more direct the sunlight, we're going to be experiencing summer. And when it's at an angle, like in the winter, when it's at an angle, that heat energy is spread out over a greater area. And therefore, we will be experiencing the heat difference, and we would be recognizing that as cooler temperatures. We call that winter. So now let's look at the Earth's orbital path around the sun. It is elliptically shaped. The Earth is closest to the sun in early January, during the northern hemisphere's winter months. This is called perihelion. And this actually occurs on January 3rd. So when I look at the word perihelion, it's just a fancy word for saying that the Earth is closest to the sun. In other words, when we say that the Earth orbits the sun in an elliptical orbit, it's not a perfect circle. And as a result of not being a perfect circle, that means it's going to get closer and be further at different locations in its orbit. Well, this will have consequences here in just a few minutes, but let's look at it just look at the distance of what an ellipse is first. And Earth is furthest from the sun in July, during the northern hemisphere summer. And this is called aphelion. So I want to make sure we are reiterating here that the Earth, our seasons are not a result of being closer or further from the sun, because we're actually further in our summer and we're closer during our winter. So we need to make sure we get rid of that misconception. And now I can look at the moon. The moon's orbit about the Earth is not perfectly circular either. It is also elliptical. When it's closest, it's called perigee. This is the word perigee, where the moon is closest to the Earth. And when it's furthest, it's called apogee. So we've got these circular motions that aren't perfectly circular. Instead, they are elliptical. So I want to make sure we understand why an object is able to orbit. And it's because of gravity. That the universal law of gravitation, and you can pause this to write this down, but I want you to make sure you get this, that the force, right, the force of gravity is equal to g. This is really teeny tiny constant. It's a gravitational constant. It's 6.67 times 10 to the negative 11th, and it's got this really funky unit of measurement, a Newton meter squared per kilogram squared. And that's not that important for understanding what's going on conceptually. But to understand what's going on conceptually, we have to understand that it takes two masses, mass 1 and mass 2, that if they are some distance apart, they will have some gravitational field. So we'll get to that in a minute. That one mass we'll call the moon, and the other mass we'll call the Earth. At some distance, here we have some distance, they have a gravitational quote-unquote pull on each other. The force of gravity changes. Mass is constant. Think about your weight. It will change. Your total mass remains constant. Look at the formula above. The gravitational constant, capital G, is very, very small. So it would be 10 zeros before this 6 here. So it's tiny. But that means something very unique that you've probably never thought of. That you have a gravitational attraction to every one of your peers. That if you're sitting in a classroom, you have a tiny amount of gravity that you're generating on every other piece of matter in the classroom, including students. So gravity and centripetal force. So any and every two masses at a distance have a gravitational attraction to one another. It just isn't very large. So if I look at the relationship here, mass and the force of gravity. If I have a mass and a mass at some distance, there'll be some gravity. If I double one of the masses, it's going to have twice the force of gravity. If I double both of the masses, it's the gravity is going to be 4 times, because I multiply m1 times m2, and it's going to be 4 times. So a couple things we need to make sure we realize. Gravity is a very, very weak force. It takes a very large mass to create a gravitational force. You're not massive enough to create this large gravitational force. And gravity is based on 2 masses and their distance away from one another. So therefore the Earth and the Moon can generate this gravitational force over a distance. So it's not like you are generating this gravitational field. You are. It's just the relationship between you and the Earth. The Earth is much more massive, therefore you will feel that one significantly more. So let's look here. Satellites in orbit. If an object is launched fast enough, it will orbit due to its continued falling into the Earth. If it is not launched fast enough, it will fall back to the Earth's surface. And this is what we call projectile motion. Well, when we look at satellites and objects that are orbiting, they are also in projectile motion. A projectile launched fast enough from Earth becomes a satellite that it's constantly falling back following the Earth's curvature. The circular path of an object moves in its orbit is generally elliptical or oval-shaped. That an object moving at an elliptical orbit does not move at a constant speed. Instead, it moves faster when it's closer to the object and slower when further away. And I can emphasize that when I look at this comet. I want you to look at this path here of this comet. It travels really, really fast here. It goes zoom, and then it slows down. And it's traveling really slow here. And then all of a sudden, as its next path around through our solar system, it speeds up, zoom, and then slows down. So we're going to look at that. And those are what we call Kepler's laws. And Kepler's laws have very, very unique consequences in this topic of circular motion. The first law of Kepler's 3 laws is called the law of ellipses, that all celestial bodies move in elliptical orbits, not in perfectly circular orbits. Because of this, the radius at different locations changes. Now, Kepler's second law is called the law of equal areas. This is a key concept here, and it's going to take a minute for you to really fully understand. So let me start. So if you can imagine each of these alternating colors as being pizza slices, that all of them have the same area covered in the same unit of time. So if I go from this location to this location, this is supposed to be like little Earths orbiting the sun. It's saying that as it travels from this location here to this location here, this area in here is going to be the same as this area here, as this area here, and this area here. It's called the law of equal areas. That as a planet orbits in equal time sections, the areas are equal. That the time to go from here to here is the same. The time from go to here is the same. The time to go from here to here is the same. This means that when an object is closest, that we call perihelion, right? Perihelion, closest of the orbiting body to the object that's orbiting. It actually travels faster to make up for the smaller radius. Notice it's closer here, so it has to travel faster when closer, and when it's further, or at aphelion, it has to travel slower. That this dark pizza slice is the same amount of pizza as this smaller, the longer and thinner. It still has the same area. That's the key. That the converse is true too. When a planet is further from the body it orbits at aphelion, it travels slower. And what's happening is we're keeping the areas constant, and that's a true story. That is what Kepler's second law says. That in equal time frames, the area covered is equal. So the time to travel from here to here, notice it didn't travel the same distance here in the same amount of time. It must be traveling slower. And it's true that the distance traveled from here to here is much larger. It's the area we're looking at. It must travel faster closer and slower further. And that's true. And the last concept we have is what's called the law of harmonies. This is Kepler's third law. That the squares of the periodic times are equal to each other as the cubes of their mean distances. Now that's a kind of fancy, funky way of saying it. It's simply saying this. That if we measure distances in astronomical units, or Earth distances from the Earth-Sun, that the average distance from the Earth-Sun is 150 million kilometers, or 93 million miles. That the period is in Earth years, and the radius is in astronomical units. The further an object is that it orbits, the greater the amount of time it takes to orbit whatever it's moving around.